Hello YouTube, this is Michael Provenzano. Today I'm bringing you a video of something cool I made. But it still needs a lot of improvement and I am currently improving it. Anyways, let's get through it. So this is the server. It's we're basically just using this bridge class I made because I made it so that it can be run either you can act as the client or the server, and you just need this class along with a couple other PGP handler, parse packet, and test proto. And I guess this one. Anyways, what we essentially do is we have three packet types. So CSE. This stuff appears these server and client. That's pretty Oh no, hold on. No, that's not pointless. I think I removed the pointless stuff, but there was like destination source. Anyways, here we get generate session ID, which just returns a string. Generate symmetric key, 32-bit in bytes. So I should probably put bytes there, but here, yeah, we'll do it. Bytes. This doesn't, like, this stuff right here doesn't do anything. It's just a comment, basically. And it also it just makes it easier to read. Like, okay, we know data is a string. The type of data, the data type for data is a string, and the function encrypt is going to return bytes. But we're not. Oh, I think I got that wrong. Yeah, we're not returning anything here. We're just... So for encrypt, first thing we do is generate the key. We get a symmetric key. Hold on. Okay, so this is the encrypt function for the actual data encryption between the lines. So we get the asymmetric key. I mean the symmetric key, and then do all this fancy stuff here, and then here no. Oh yeah. F.encrypt. This is the actual data that's being encrypted, and then we turn it to we make it a string, and we do some magic here just to make it to remove the base 64, because this module right here, Fernet, it encrypts stuff, but it turns it to base 64 and then byte array, not a byte array, bytes. So it literally looks like base 64, but it's in bytes. So if you look at it in a hex editor, it just looks like a string. Ridiculous. Anyways, here's where we actually build the packet. So yeah, these two, a host name here and host name here. No, those we're still using those. I should actually probably put self.server, self.client here. Since okay. Okay. Where? Here. Okay. Yeah, so here's where we okay. Let me actually open this because what are we doing? Test proto. So all we're doing is just setting these variables, and then we are running full data type. Are we running the encrypted version? Yeah, encrypted data. So this just basically builds the packet and puts it into a byte array. It just appends byte arrays. It's just a list of byte arrays. I guess append is the right word. And then we set full data to the combined byte array. And as you can see here, we then send it, self.socket.send encrypted packet data, and then we increment the packet number, and then sleep one, just make sure that it gets there. Hold on, I just thought of something. In one of my programs, I implemented a timeout checker. So it would like send a packet and then calculate or time it and see how long it took to respond, and based on that, it would set the timeout, which was super efficient. I mean, I don't know if it was super efficient, but it, you know, it was pretty accurate. You know, if you only need like 0.5 of a second or 5 nanoseconds or something, I don't even know. And the decrypt just parses this encrypted packet, and then we verify the checksum. If it's not verified, then we exit. It's pretty cool. I did mess around with this by intercepting a packet and changing 1 byte and then sending it back, and it just exits. It's pretty cool. Anyways, we get the symmetric key. We then decrypt the data, and then the client bridge is pretty interesting. We first build a packet using the C mode, and this basically says to connect. And then here we build the data, and then here we actually send the packet. We increment it, and then I want to make this kind of fast because I'm gonna leave at night. Anyways, then we wait 0.5 seconds, and then we expected server public key. We received something. It's basically a 3-way handshake. Diffie-Hellman key exchange is what it is. And then, yep, we get that. We verify that it is that. We verify the checksum of the received packet. Yeah, here we parse it, and then we do that. And then we do some PGP stuff to decrypt the private key. The public key. Don't ever send your private key to somebody. And then once we decrypt the private key, the public. Oh, hold on. Once we decrypt the server's message, we then check the packet type, make sure it's S. If it is, then we continue on. So then we generate the symmetric key, because now we have now we have the server's public key, and the server has our public key, so we can safely encrypt stuff. We can safely send the symmetric key. This is extremely similar to SSL. And hold on. Yeah, we generate the symmetric key, and then we encrypt. This is PGP stuff. So we're encrypting the symmetric key with the server's public key. That's what this function does. And then we build the actual packet, and for the data, we just set it to the encrypted data here. And then we format it, and then we ship it off. That's all the client does. And then the server. What the server does is the first thing we do is receive some data, and we check if we receive some data, then we parse the packet, verify the checksum, and if the P type is C, which it will be because we sent it up here, then we will set the data. The server will extract the client's public key. Now, we're going to set up some PGP stuff and encrypt our public key, the server's public key, with the client's public key. And then we're going to build the packet with the S option, S packet mode, and we'll format it, and then we'll actually send it, and then we'll update the packet number. Expected encryption. I labeled these variables so nicely. It's so easy to tell what's going on. Not really, kind of. Okay, yeah. So we get the encrypted packet, and we decrypt, or we parse the packet, verify the checksum, and then if the packet type is E, then we decrypt the data. Then we set this. Then we decrypt the client's packet, and it should be equal to the symmetric key. Now, that's all it does. All these two functions do is the three-way handshake. And then we have this encrypt and decrypt function, which we're actually going to use. So here's the public key, here's the private key. It doesn't really matter too much because this is just for testing purposes. And we have the key, secret key for the PGP. And host, we just do IPv4, TCP, bind 999, listen 5, except the usual stuff up here. Then we set this bridge class. I just have a bunch of random crap because these two are completely pointless. And then I was going to do something, but I'm going to implement it into this one. You see, it's basically, it looks like Tor, kind of. Source test, prox 1, prox 2, prox 3, and then I got a bullshit IP. Almost exactly like Tor. But I want you to have the ability to go through multiple computers without me setting these variables all the time. Okay, and then let's go down. Yeah, public key, private key. And then we set the bridge client, and then S is the socket. What is it called again? Class? Object. This is the socket object. We're passing it here. Now we can use it inside of the class. That's why it says self.socket.send. Because s.socket.send. And then we do bridge client, private key, right? Client bridge. And then in the server, what we would do is basically the same thing, but set up a server. Use the bridge class. Use the bridge object. I don't know. I forgot the terminology. And then what we're going to do is do server bridge. Right. That's just what those two functions are gonna do is basically just give us a symmetric key securely using Diffie-Hellman. And then we can encrypt stuff using symmetric key. Using the symmetric key. But for now we're just using AES 128 CBC mode. I want to use a different Galileo counter mode. Galileo's counter mode is the one I want. Galileo's AES and Galileo's counter mode is I've done quite a bit of research on AES, reading books and stuff, and not reading books, but reading chapters. And it seems like Galileo's counter mode is one of the best. But they say it's hard to implement yourself. We'll see about that. Am I even getting audio? Oh, yeah, okay. Yeah, and then, we just encrypt stuff. And on the server, we just forever, while true, just try to receive data, and if we do receive data, then decrypt it using our symmetric key. Now, let's actually run this. I'm going to open up Wireshark. Hold on. My computer does not like this. Galileo's counter mode. We're gonna open up Wireshark. I only have 4 minutes left. Okay, what we're going to do is do loopback address. Loopback. Because it's got 127.0.0.1, and then it's got the IPv6 for 1, and this just that's my MAC address. Gonna have to blur that out. Fuck, I can't just upload this. Okay, so now we're receiving. Now let's actually run it. So what we will first do is launch the server and then run it. This is just it's just an error message from the PGP library I'm using. The PGP library is terrible, but it works. It's just coded so fucking horribly. There's a way to disable this. but I haven't figured it out yet. I could definitely manually just remove these fucking print statements. Or, not print statements, but remove this line. Just set it to, like, something that won't give us errors. Anyways, as you can see, we received secret text. This is a new packet text. This is a new text packet that should be encrypted. Oh, I should stop the Wireshark ages ago. Okay, now we are going to open up Wireshark. What we're going to do is go to the first TCP packet, and we're not using this. Let's start at 1. We need to set the stream. The stream, we need increment through all of the TCP streams. So, oh, here it is. So this is the actual data we're sending. It's pretty cool. PGP, public key, and the server encrypts a message using the client's. The server encrypts its public key with the client's public key. Then we send it back to the server, and then the client decrypts the server's message and obtains its public key, so we can then send the symmetric key using the server's public key. And then this data down here is the actual encrypted data. Now we got a hex dump. We can see. You can see it all down here. And then these bytes up here are ones I'm actually programming. So as you can see the E, you can see the S, and the C. Now if we exit out here, let's see if we can see it. Okay, this is one data. Okay. Yeah. So, yeah, usually when you send something in Python, it does it immediately at the data. But I have reserved these parts for specific options all the way up to the message. Now, what I basically mean by that is if we take a look at the actual build headers, the headers. That's not. Yeah. So these two are. So the only thing we're doing is setting the P type, the mode, packet number, checksum, data length, and data. We have a bunch of useless crap here. Now I'm going to show you how I've improved it a bit. For starters, one thing we can see is that there is a shit ton of overhead. We have a 3-way handshake. Cincinnati, and then we have this. I don't really know what this does. I looked it up, but I forgot. And then we have the actual data, the push act, and then we have to send, and then it sends an acknowledgement. Then we send some more data, and it sends an acknowledgement. And then at the very end, when it's done, it sends a fin act, so it finishes, and then it acknowledges that we received that packet. There's way too much overhead, although it is pretty reliable. Okay, so we got that out of the way. So in the new one, here it is. What I'm actually doing is just setting a UID, a mode, the data, and a checksum. Except the checksum's right after the mode and the data's on bottom. I have some utilities for the class, so we can do character to int, but it's actually byte, character to byte, and then int to byte, and then string to byte, and then generate UID, which is an 8-character byte array. And then here we have the tight handler. That's pretty cool. This is the comment I added, the doc strings. And then we set up an init method, and then I use this to set up the init method in the data class. And the full packet is nothing. So we have the string method, which basically, I'm not going to go over the entire thing. But as you can see, to build the actual packet, we just make sure the data is not a byte array. And if it is, then we do strings to byte array. Now we set the UID, the mode, the checksum. all that stuff is being set to bytes. Because remember, we set all this stuff up here. All returns bytes. So then what we actually do, the checksum is pretty cool. I have to add everything up and then do H. And then the full packet is literally just all the byte arrays appended to each other. And if we actually parse the packet, I did it pretty smart. It was pretty clever how I did it. Actually, not really. It was normal. This is how anyone would do it. I just put them all on a line and then we unpacked it right. And then for the data, we just did the last 12 bytes. And parse the packet. I set up an HTTP packet. So this HTTP packet Wireshark doesn't actually pick it up as an HTTP packet. Like, it won't say HTTP, it'll just say TCP. But we will get, if we send this packet, we will receive a response, an HTTP response. But it's weird that Wireshark doesn't see it as one, even though I copied the important stuff byte for byte. We could actually do it byte for byte because we have the bytes because it's being sent in a byte array. Anyways, so I just basically set the host, the get path, the protocol. Yeah, I guess verb path protocol. And then we set the host. These bytes were very specific. We set the host, application type, we set the content type, user agent. The user agent was pretty important, and then the data. And what this basically does is it allows us to send a GET request with the data appended. So what I'm thinking is, what if we sent what if we encrypted the data in the HTML or something like that, or built another packet inside of HTML and like had it do polymorphism with the page building. That'd be so cool. It's something I could do, which is even better. Yeah, so this is the type protocol. It's the new protocol, the better one. Here I'm building a new one. I want to build a proxy protocol on top so we can actually like proxy. So we can go through multiple computers instead of just doing peer-to-peer. And then here we have the actual bridge. I haven't built it yet, but as you can see, all we need is just the message. And then we do HTTP encapsulation. So we set the host name and we add the packet to the end. And then we parse the HTTP packet, we print the data, and we connect to an HTTP server. And the data we send, so just connecting to the HTTP server will just initiate the three-way handshake. This is at the socket level. So we're sending it at the transport layer, which is pretty cool. We're sending data so this is just the transport layer, TCP, UDP, and a couple other ones like Quick, and I don't remember the other ones, but we send it on the transport layer, and then we go to the application layer. Now, we're not going straight to the application layer. In this case, we're going to the presentation layer. That's where all the data is being added in the presentation layer, and then we parse the application. Yeah, so this connects to the transport layer, and we send data only up to the presentation layer, and then we close, and then we parse the packet, and then we print it. It's pretty important that we never actually get to the application layer. It'll just be better security. Well, not really security, but security throughout obscurity. And yeah, that's about it for now. This is a really fun project. As you can see, I have a bunch of files I made. Just like experimenting, like this one's I'm gonna be using UDP, so I just named it UDP. And yeah, I'm experimenting with adding it to other protocols, or smuggling over multiple protocols instead of just TCP. We can now do HTTP. I want to do ICMP next, and then DNS. And then maybe if I can, and then, I don't know, I want to try SSH or something like that, or maybe 25. I mean port 25 when I said that. That's about it. Like, comment, and subscribe.